All right. Hello everyone again. It's me again. So this time I'm going to do the analysis of the CodeJam 2020 round 1C, which again I didn't participate because I already passed round 1A, but I just did it for fun and the questions look really interesting, aka the stay home program. So yeah, let's get started. So the first problem. So basically, what it says is that so you are standing at 0 0. Okay, the question statement is very long, by the way. uh you are standing at 0 0, and you have a target which is at coordinate xy right now, and x and y are here. It looks like they are positive, but it doesn't really matter. And every time you are allowed to move one step, meaning that your coordinate will change by either your x or your y coordinate will change by one, but not both, or you are allowed to just stay put at your own place. On the other hand, this target, which is Pepper, it has a tour that starts at the xy that I said just now, and then it has a tour of length m, and during this tour you are allowed you are required to like choose any point at any time where this target lands at, and apparently you take a photo with this target, and then you are done. But you have to do it in the tour itself. So so the question asks, how soon can you do it if it's possible? Meaning that if I can do it at time two, and I can do it at time four at the same time, I want to prefer time two. So let's get started. So in this example, it means that the xy, the original coordinate is 4 4, and the path is it will go south all the time, which means that it will become 4 3 4 2 4 1 and 4 0 after 4 seconds. It turned out that you cannot meet your target within 3 seconds, but you can do it in 4 seconds, so the answer is 4. And the second one means that the target is going from 3 0 to 3 -1 and 3 0 again, 3 1 3 2, and after that the target is gone. So it turned out that you cannot do it in 4 steps, so the answer here is impossible. So yeah, let's get started into the analysis of the solution. Okay, so to know to know the intuition, right? Let's say the after let's say s seconds, the target will be at xs and ys. Okay, then how do we know that after s seconds we can travel to this point xs and ys? So recall what I said. We at every time step we are allowed to move one step, or we just stay there and do nothing. So it makes sense to think of that. Given these operations, what are all the steps that we can that we can that we can land at after s seconds? But we can't afford to try all s seconds, because all the sorry, not all s seconds, to try all possible possibilities, because this will just be wasteful. So instead, what we could do is that we introduce this thing called Manhattan distance. Okay, so there's this theorem that says that so what's the mean so before that, what's the meaning of a Manhattan distance? The Manhattan distance means the absolute value of x xs plus the absolute value of ys. Okay, that is the Manhattan distance. So there's a theorem that says that within let's say within time step t, aka t steps, if we land at xy, then the Manhattan distance of xy must be less than or equal to t, which makes sense because the Manhattan distance is also the horizontal and or the vertical distance of the sum of the horizontal and the vertical distance of a point from your location. And if you want to prove to yourself more rigorously, you can show that the Manhattan distance of you and your target square, say xs, ys, changes by 1 for every for every step you make, which means that you can change by at most 1, which also means that you can decrease by at most 1. So now the strategy is to find x as the minimum s and minimum s such that find the minimum time s such that after s seconds, pepper lands on s, xs, ys, and the Manhattan distance is less than or equal to s. Okay, so once we know this, it is very straightforward because we are given the direction, so we of every step we can keep track of the direction as what we did just now. So if you look at the first example, 4 means it means that after 1 second it becomes 4 3. Check the so yeah, you know what, let me just write the test case here. Okay, so 0, 4, 4, the Manhattan distance is 8, which is no good. After one step, it becomes 4, 3, the Manhattan distance is 7, which is also no good. Yeah, we'll just continue. After 2 seconds, it becomes 6. After 3 seconds, it becomes 5, and after 4 seconds, it becomes 4, which is exactly what we want. And so when I say that just now, this the fact that xs plus ys, the absolute value must be less than or equal to s, it is not only necessary. It is also sufficient, because we can show that there is a way to go to the point xs ys within the time, which is also the Manhattan distance. So how do you know that? How do you do this? So let's say we want to go to, let's say, for -3. We will walk 4 steps to the right and 3 steps to I should say 4 steps to the east and 3 steps down, which is to the south. Okay, once we go to the south, once we reach that in 7 seconds, we can just stand there and wait until until Pepper comes. So this is pretty straightforward, I have to say, and there's honestly nothing much to the code, except that we update the x and y location after every second, and we check whether the absolute value of x and y plus absolute value of y, the Manhattan distance, is less than or equal to I plus 1. So yeah, this is pretty much straightforward, I have to say. Let's make sure also that I started recording. Okay, nice. The second problem is, I have to say it's kind of cute because this is the question that you don't even bother to prove. You just rely on your own intuition. So what it means is that okay, so how it works is that you have you have a string D, 10 letters. Let's say let's say it is let's say the string is, or this thing I should also say, let's say it is named as CodeJam Fun. Okay, so but we do not know what is D, but instead what we could do is that that's we like for like at each step we do pick a number m within a range, okay, and then uniformly. This word uniformly is very important in this question. You'll know why later. And then the second one, pick a number n, 1 less than or equal to m, less than or equal to n. So this is also 1 less than or equal to m, less than or equal to limit, and then encode n. So what I mean by encode is that, let's say n equals to, n equals to 3501. So 0 means so this means 0, C is 0, O is 1, D is 2, N is 9. Here, since 3 corresponds to E, then we do 3 to E, and then A is 5, and C is 0, and O is 1. So the encoding is E is 0. Okay. Now the question is that there are two parts of the question. Given M, like a sequence of M's, and the encoding, the strings, not the ends, recover D. Okay. The second one is that M is never given. Only the encodings recover D. Now, if you look at the second, even though for the first one you know what is M, you do not know what is N, so it kind of doesn't make sense to guess what is D, right? But the point is that both the selection of M and N is uniform. Okay, so let's solve this question in two ways. The first is first is intuition, and the second one is math proof. Okay, the first thing we know, the first thing we want to see is that now we are by the way, for both of them we have like the 10,000 sequences, be it M or the first part or second part. The first thing is that if we look at this one, there cannot be any leading zero. So N cannot have leading zero, which means that the first one, whichever letter that becomes the first one, cannot be zero. Okay, that this one I hope I don't have to repeat it. Which means that if we look at all the encodings, the first letter, then we know that it is it has to be 1 to 9, and we just have to hope that this 1 to 9 contains all the 9 distinct characters, and somewhere else you will find a 10th character, and the 10th character you know that it has to correspond to 0. The second thing we want to notice is that okay, before that, let's talk about some very intuitive thing. If this limit is small, if let's say u equals to 2, so the limit is 10 to the u minus 1, which is 99, then we can hope that some of the m will be a one digit number like 1 to 9, and then from there we can guess like what is uh sorry, this should be between n and m. Then we can guess, okay, let's say m equals to 5, and 5 correspond and then so and then your encoding is something like c. Then you know that this c must correspond to either 1, 2, 3, or 5 to 4 or 5. Even luckier still, if your limit is small enough, then you pretty much will have all 1, 2, 3, 4, 5, 6, 7, 8, and 9. Then if m is 1, then you know that n is also equal to 1. If m is 2, then m could then n could be 1 or 2. So once you know that if based on the case where m equals to 1 and you recover the first encoding, you just have to look what corresponds to the second encoding, which hopefully exists, and the third encoding, and then you do the same thing for m equals to 1, 2, and 3, where the third, then you know what is the third encoding, hopefully fourth and all the way to the ninth one. Yeah, but this is very unsustainable. So that for two questions, not two questions, two reasons. Number one, for the second test case, u equals to 16, which means that you can have like 99 dot 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 9, which will be 10 to the 16, and you only have 10 to the 4 queries. So I can't really guarantee that you will get at least one digit number even. The second thing is that if you look at the last test case, you are not even given m. So from here we have to do something else. Okay, now here comes the intuition part. We know if we think about the case where m equals to, let's say 2000, then half of the chance n is between 1000 and 1999. And if you think about it, right, 1000 to 1999, the first letter is not the first letter, the first number, the leading number is 1. And if you go a bit further, let's say your m is 3000, then 1/3 of the chance your leading number is 1, and 1/3 of the chance your leading number is 2, and etc. etc. So you can kind of guess that leading number 1 appears the most often, and this is true because of the reason that I said just now, and there's also this theorem called the Burford's theorem. So if you look at the analysis, one version of Burford's law, you'll see that the leading number 1 will appear the most times, and it just decreases according to as your leading number increases. So if we know this this pattern, then all we have to do is to record all the leading characters and also the frequency. Sort them from high to low, and then this correspond to 1 to 9. So let me just jump to the code right now, and that I submitted. So yeah, like from here, these are the 10,000 queries that are given. So this R is the string and Q is the MIs, but in some cases Q is -1, which means that they don't even want you to know what is MI. But never mind, you will see that all the solution here doesn't even use the Q, and therefore from if you look at what's R0, it means that we record the frequency of the leading character. So yeah, and this all charts is only to see like what is the character that doesn't that appear, I mean it appears somewhere in the string but not as a leading character, like never. Then we know that this should be 0. Okay, and of course what I've said just now relies on the law of large number, because if your sample size is small enough, then none of the ends, which is a pre-image of encoding, none of the n even has a 0, so which means that the digit 0 does not appear anywhere. But you can probably imagine that this probability is very low, because we have so many queries. I will leave you to think, you to figure out what's the probability if you are interested. And now comes the math part. So how do you justify that the leading number 1 appears the most often, and etc. So this is not that really essential to solve the problem. Let me see what if I use it. Yeah, this is not really essential to solve the problem. I'm presenting this only out of mathematical interest. So if you think about it, right, then the first thing we need to do is to find the n equals to some number n 0. Okay, we need to find what is the probability. If you think about it, right, the m is uniform, so m could be 1, could be 2, could be 3, could be 4, all the way to the limit. So when m equals to 1, okay, m equals to 1, right? Then we know that this is 1 if n is 1, 0 otherwise. When in general, if it's given an m, then we know that this probability is 1 over m if n 0 less than or equal to m, 0 otherwise. And this one, by Bayeson's theorem, it is also the same as it is also the same as here m means that the number we have chosen, the first m we have chosen is m. This is and because the queries are independent, we can actually split that and get something like so what is that, what is that called? Sorry, I not independent. Yeah, so yeah, this thing is 1 over m, which also means that, yeah, sorry, let me correct myself. Okay. Yeah, sorry, this is the first time I'm doing something like this because I don't have a whiteboard. Yeah, so I have to result in this method. Okay, enough gibberish. So from here we know that the probability of m m is a given m and n is n naught is the same as the fraction 1 over m times p of m, and this p of m is is uniform across all m equals from 1 to the limit. So, and the limit is 10 to the u, so we know that this is the same as times 10 to the u, which then means that the p the probability where n equals to n of n equals to n naught is the sum of this expression from m equals to n naught all the way to 10 to the u, because m cannot be smaller than n naught, and therefore this thing is the same as one 1 over m times 10 to the u, the summation from n naught to 10 to the u. Okay, so now once you find this, right, you might also want to sum it up, but this is a bit hard to sum up. So if you think about integration, where you integrate the sum of 1 over n naught and 1 over n naught plus 1 all the way to 1 10 to the u. Sorry, this should be 10 to the u minus 1. But it doesn't matter anyway. We will just, so we will get something like the ln of 10 to the u minus the ln of what's that, and how do I get this? So this expression, I approximate it with yeah. So this should be 10 to the u minus 1, but we are just interested in what is the limit. So yeah, it's almost the same as the integral from n0 to what is that called, 10 to the u 1 over x dx, which is and then you can just approximate 10 to the u minus 1 with 10 to the u, because it is the difference is pretty small when u is big, and you'll get this. Okay. Yes, so this is the probability that we are looking at, like approximately, but yeah, it will add up nicely later. Okay, now we want to sum this up across the same digit, the same leading digit. So for this purpose, we will only we'll only focus on the same leading digit for the same number of the same number of what's that called, the same number of digits. So we do this for, let's say, we do this for 10a times 10 to the k less than x less than or equal and smaller than 10 to the k. Okay, so we want to sum this expression up in this range, which, if you think about it, turns out to be just plug in the summation. Okay, m equals to like what? Okay, let's do n not equals to this, and okay, and this can be approximated again using the power of what's the power of integration. And it turned out that this, okay, so this doesn't unfortunately doesn't have a nice expression, but it will turn out that this is the same as 10 to the power of k minus u, u minus k ln 10 plus 10 to the power of k minus u minus 10 to the power of k minus u a plus 1 ln a plus 1 minus a ln a. Yeah, so this should be this symbol. Okay, so this thing is the last expression is the approximate result of the integral that you are looking at, and we want to sum this for k equals to 0, 1, 1, 2, all the way to u minus 1. Now, summing this up could be a bit annoying, so and also we assume that u is really big. Like for this purpose we are only interested in the asymptotic result. So all we need to do is that if you look, first of all, if you look at this one, we can write u minus k as m. So this is the same as m. So this is minus m, and this is m. This is minus m, and this is also minus m. Okay, now so this is also the same as m equals to 1, 2, all the way to u. But if we want this thing to be independent of u, as in that we assume that u is really big, then we might as well take u is as infinity. So we can actually sum this up as the sum of m equals to 1 all the way to infinity. This expression, and if we still remember our geometric formula, then the sum of 10 over m, the 10 to the power of negative m for m from 1 to infinity is 1 over 9. And if you multiply this by m, then just do some differentiation in respect to m in this, you'll get this as 10 to over 81. Okay, yeah, so if you do some differentiation in this part, then you will get that this is 10 over 81, which also means that we can simplify this to something like 10 81 ln of 10 minus plus 1 over 9 minus this whole fraction. Sorry, not the fraction, it's equation. But yeah, divide the whole thing by 9. And this is precisely the probability of leading digit equals to 1. Leading digit equals to a, where a equals to 1, 2, 3, 4, all the way to 9. Okay, so yeah, this is a probability where the leading digit is a. And if you want to see what is the magnitude of this, I have also written a Python script. So let's do it. Okay. Oops, I need to import math. So yeah, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you can see that there is like a noticeable decrease in the number. If you are actually if you are actually curious on seeing how whether 10 to the 10 to the 4 sample is enough. I've also written something something like this, as in that, okay, so let's say n is the number of digits. So we should in the question, it is actually u, and then we calculate we calculate the probability of each leading digit. So which gives us this score variable, which is also aka the probability. Then here we just want to compare like what is the probability where like in your 10 to the 4 queries, supposedly the number of ones should be more than number of two, and then you get something very different. So here I also calculate the standard the standard deviation, as in like I calculate the standard deviation based on the binomial where based on the binomial where the first digit is either 1 or not 1, and then 2 or not 2, and then you sum this standard deviation up and divide by 10,000 as the standard protocol. Then you get the z-score, and you get and then you get the p-value. So let's see what would the p-value be for each 1 and versus 2, 2 versus 3. We only compare the what's that called, the adjacent numbers. So yeah, Python random check.py. Okay, let's say we want 2 digits, and you can see that the probability, the best you can get is when you have 8 versus 9, which is 1.07 over a million. If you go something like 10 to the 6, then they are kind of the same, as in like the probability goes a bit bigger, but still in the one in the like a few in the million range. So you are pretty safe in this case. So yeah, this is this is the mathematical editorial that I have. So the last question is also very interesting, I have to say. So what it says is that you have a certain number of slices of cake of pancake, and then each of them is circular, meaning that it is the size is proportional, the area is proportional to the degree, and all the degrees are really different. And then you also have D diners, and they demand that all the slices they want they get have to be the same size. So what you can do is that you have all the slices, and you can cut off some of the slices, so that in the end you have like D equal slices to give to your diners. You want to do this in a way to minimize the amount of cut. So let me write down the number, the rules. Okay, so n slices, D diners, requirement. Cut the slices such that you have D equal size slices. You are allowed to have leftover. So for example, let's say you have like 5 and 9. The slices n equals to 2, D equals to 2, and then you have 5 and 9, the slices. Then you are allowed to do like 5. You are allowed to do like 5. Give 5 to one of the diners. Then the other one you do like 9 equals to 5 plus 4, meaning that you give you cut it into 5 and 4. Give one the size of the slice of size 5 to your diner, and the last one you the 4 you keep it. That this is allowed. You don't have to use up all the slices. So yeah, let's think about it. Let's think about this one. If you look at each size, okay, I should also say cut the slices using minimum cut. Okay, so let's say for each slice you want to tear it into k smaller slices for your guess, where k is less than or equal to d. How many cuts do you need? Okay, so here's the thing. If no leftover, then you only need k minus 1 cuts. Because if you cut it into half, then you only need 1 cut. If you cut it into you cut it into thirds, then you need two cuts and so on. But if there's leftover, then you need k cuts, meaning that let's say you want to cut your pancake such that, like, let's say 10 of them you give to your guest, and then you also have leftover. Then in this case, you have like you already have like 11 slices, just that not all of the same are given. Not all of them may be the same, and not all of them are for the guest. So yeah, then in this case you have k cuts. So if you think about it, right, the goal is the same as giving as many perfect slices to your guest. Okay, why do I say that? Because if there is leftover for each of the slices that you cut to your guest, then you have the cuts for additional cuts. Whereas let's say you have let's say d equals to 20, and then 10 of them are perfect, it means you have no leftover, and then if you do the calculation, then you know that you only need 10 cuts instead of 20. So the goal, as what I said just now, the goal is to give as many perfect sizes to your guests. Now, one thing, this question, it will make you think that I don't even know how to start approaching the problem. But we can first see what is an easy bound. So what is an easy bound? It is d minus 1. Why? Because we can just choose any one slice and then cut it into d perfect cuts, which means that you only need d minus 1 cuts. So this also means that for any optimal solution, at least one size has to be optimal. And from here, we already narrow down like what is the size of each pancake. So what we could do is that we cut all possible sizes of your gas slice. So how do I do this? How do we do this? This means that choose one piece and cut it into k perfect slices, where less than or equal to k or less than or equal to d. So this takes what's it called? This takes size n times d. Sorry, time O of n times d. Probably with log factor, maybe, I guess. So yeah, let's do a tilde. So it doesn't really matter because it's just n times d. So the second one is that right now we have all the possible sizes of your guest slice, and from here we also know that like let's say let's let x to be a possible gas slice size. Okay, and from here we can also know that which so from here we know two things: which slice from the n slices. So gas slice means after you cut, after the cut. Slice means before the cut. Okay, from the n slices that can produce perfect what's it called? Perfect slices of size size X, and then how many slices are there. So let me put an example. Let's say your original slice is 3 and 6, and then we know that 1 or let's say 1.5. Then okay, let's just use 1.5 because I want to show you that they allow fraction, which is also annoying in some sense because you might deal with floating point, which is bad. Yeah, I will show you my solution later. Okay, so this is slices is 3 and 6, and then guess size possible candidate is 1.5. Okay, so the meaning of 1.5 means that the first slice is okay. We can produce 1.5, and then we need 2 smaller slices, and then the second and then for the second slice, yes, and then here we need 4 smaller slices. Whereas if let's say we have 8 here, then third slice, the answer is no. So and therefore we this is the bookkeeping that we need to do, which is still okay. Now we need to see how do we do the optimization. Okay, so in this case, right, we need like 2 in order to use up all the let's say we decide to take 1.5. Okay, so if let's say we are going to go with 1.5, then and we want to use up all the first and second slices, then we will need at least 6 gas in order to fully use all the first and second slices. And this gives a question: how do we maximize the number of perfect slice that we can give to our guests given the number of guests? Okay, so in this case, right, we need at least let's say we only have like 1 guest, then we can't really use any of the perfect slices. If our guest slice is 1.5. If we have 2, then yes, we can use the first slice, and we need 6 in order to use both the first and second slices. So let's plot another example. So guest size is I don't know how many. It doesn't matter. So the first one, let's say we need like 3 smaller slices. This one we need 4 smaller slices. This one we need 2 smaller slices. Then from here we already know that we need at least 2 gas in order to 1 perfect slice. Then we need at least 2 gas. And if we want 2 smaller slices, then from here we can see that we need 2 plus 3, at least 2 plus 3. So the minimum of any 2 sums, then it's 5. If we need all, when we want all 3, then it has to be 9. Then 3 slice, it has to be 9. So here we can intuitively we know that we will just go from the smallest all the smallest slice all the way to the all the way until we run out of gas. Then from here we determine how many slices that we can give to our guests. But there's also another caveat. So we go back to this place, this example where the guest size is 1.5 and the slices are 3, 6, and 8, as aka we only have 3 slices. Then the third slice, if we want to do it to cut it into 1.5, right? Then we can only have at most 5 smaller slices plus leftover, which means that if we have 12 gas, then this whole thing is invalid. Why? Because we can't even produce we can't even produce 12 slices that are that have each have 1.5. Okay, so the last thing to check, we can produce at least these slices, guess slices of a given guess possible guess slice. And how do you check this? So if we just check it naively, we will turn ourselves into the O times O(n) square d solution, and this is very inefficient because if you look at the last test case, d is way smaller than d is only 50 and n is 10,000. So this is bad. So instead we think of this observation. If d is really small and we have a lot of slices, then let's say if at least d of the slices are big enough, then we get to cut at least get to cut at least d slices just from the just from the what just from the slices itself. So yeah, if we have d of the at least d of the slices are big enough, then we have d slices guess slices of a given guess slice. So that happens if n is really greater than d. So all we need to check is that the d biggest slices add up to at least add up to at least d slices, because if we don't really have d that slices that are big enough, then and as soon as you know that there's one slice that is less than the guess size that we want, then we can just discard the whole process. So let me put things into words. So let's say your guess size. So let's say your guess size is let's say 35, and I know this is very big. And let's say your slices are, let's say 3, 4, 5, 8, 20, 35, 70, 105. Essentially, we don't really have to check all these things, and instead we only have to check this one. So this gives another algorithm, as in that we only check at most d of the slices. Okay, what happens if we know that we have at least d they have at least d of the slices that are big enough? Then we know that this whole algorithm is valid. So this gives this in terms gives an ND square solution, which is pretty good because the d is small in this case. Also, and this also means that we have to probably sort the slices first. Okay. So yeah, that's all the solution. So let me repeat this. Let me repeat the steps. Okay, so record all the possible slices of the sizes of your guess slice. This will take O of ND what, and then for each of the possible guess slice, we check we also check like how many smaller slices each slice that can give this perfect guess size will be required. So in this case, we have 2, 4, and 5, and whatever. And all this number of slices, there are only like n times d of them, because we have n slices and we have like d, and then we have like d possible guess. And finally, we also want to check that we can produce at least d guess slices of a possible given slice. Then from here we will from here, this whole process will be O of ND square. So yeah, this concludes the verbal solution. And yes, let me also show you the my code. Uh, the the thing is that we know that the size can be a decimal number. So using floating point is really a bad idea in this case. So instead we will just use a rational number, which is why you can see that there's this GCD helper function that helps us to simplify. Like this one, we want to store it in a simplified function. Simplified function, and here we also store something like the lookup of we also do like a map of the the rational number to a list of how many like how many slices we need, smaller slices we need to keep. So this is reflected over here, and d minus answer equals d minus 1 is just like the easiest bound that we can guarantee without using our brain at all. And then this just means that if the count means that we can like how many perfect slices that we can produce. If it's less than d, then we just don't care about this part. As long as this is more than d, if you can see here, we will need to break out in order to keep ourselves in the ND squares and in the ND square solution. And finally, this part just is just to it's just to keep track of how many perfect slices that we can give to people. And yeah, that's all about that's all my as solution. Yeah. Before I end, yeah. Thanks to the CodeJam CodeJam organizers for the fantastic problems this time. And round 2 is coming up in 2 weeks. So yeah, I'm hoping for the best for myself. Yeah, and stay home, stay healthy, and let's keep flatten the curve, squash the curve, and yes,